Hello, my name is Louis-Guillaume Gagnon. I'm a postdoctoral researcher at University of California, Berkeley. I am affiliated to the ATLAS experiment, and as part of IRIS-HEP funded work, I work on ACTS, which is a short for a common tracking software, which is a toolkit that we use to reconstruct charged particle trajectories in particle detectors. And today I want to tell you about a subject that's called cluster merging. So implementing cluster merging in the ACTS exam. So first of all, what is cluster merging? So a charged particle passes through a silicon module and the detector. They will transfer energy to electrons in the bulk. When these electrons then drift toward the pixel sensors, then when they get collected by the electrodes, it generates a signal. But typically, for a given particle, you will see signal in many pixels. That's due to a couple different things, such as stochastic diffusion in the silicon. Just the charge can drift because there's usually a magnetic field in the detector, or it can even be something called delta rays, which are just like electrons which are kicked very far from their original positions in the silicon sensor. And so you have a picture of what that usually looks like on the left here, where we have these three particles, which each have illuminated different sensors. However, when there are lots of close-by particles, these clusters can then have contribution from multiple particles. We see what it looks like on the right here. So the particles in that case were very close by, and we only can see a single charge clusters which has contribution from these three particles. So that's what we mean by merged cluster. Now, why is it important? So first of all, there's an effect that's due to relativity that goes like this. So when a heavy particle decays into lighter particles, then the decay products of the heavy particle will tend to be collimated in the direction of light. And as a consequence, if you have collision events in which heavy particles are produced, they are just more likely to lead to merged clusters in the first few layers of the detector, just because of the angular distribution. And we have many hypothesized beyond the standard model physics theories that we're looking for in the LHC, and that may very well lead to production of such heavy particles. And so we absolutely need to account for this effect in simulation. So I just wanted to give on the bottom of the slide an example. So in the standard model, we have a particle that's called the Z boson, which has a mass of about 91 giga-electron volts. And there's a hypothesized particle called the Z prime, which would be kind of like the cousin of the Z boson, but much heavier. So we see that the graphic here shows you kind of the probable masses, that's the x-axis, and then the y-axis gives you the cross-section, which is related to the production probability at the LHC. And so we see that this cross-section is not negligible up to very, very high mass. The x-axis has units in TeV, and 1 TeV is 1,000 GeV. So these particles can be extremely massive. Okay, so how do we account for that? So in ACTS, we have a fast particle trajectory simulation module called FATRAS that takes particles that are generated by specific software and then simulates the energy deposits in the detector. And then on top of that, there's a digitization module which takes these energy deposits and turns them into discrete signal from sensors. And as it is now, this module only creates signals looking at individual particles. And so if the particles are close by, it will not merge. They're different clusters. So as part of IRIS-HEP funded work, I've been implementing a first version of such cluster merging on top of the digitization module. And we can see some of the preliminary results here on the right, where on the x-axis, You have the module density, which is just the number of charge clusters per square millimeter on a given module. And then on the y-axis, you have the average number of merge clusters on that module. And so we see that for module where the density is much higher, then we find on average more merge clusters, as we would think. And so the next steps for this project would be to implement accurate particle position estimation in clusters, many particles, and with accurate error estimation on top of that. And we also want to port this code to the ITK specific code of the Atlas collaboration.